Question 1. What are conductors, and can you name some common examples of them? Conductors are materials that allow electric current to pass through them, with very little resistance, or sometimes, with almost no resistance at all. Examples of conductors include gold, silver, copper, aluminum, iron, zinc, charcoal, and ordinary water. Question 2. What are insulating materials, and can you name a few common examples of them? Insulating materials are substances that offer a very high resistance to the flow of electric current, and prevent electricity from passing through them easily. Common examples of insulating materials include paper, glass, mica, porcelain, rubber, air, and distilled water. These materials are widely used in electrical systems, to improve safety, prevent electric shock, and stop unwanted current leakage. Question 3. What is electric potential difference, or voltage, and what is its unit of measurement? Electric potential difference, also known as voltage, is the electrical quantity that causes electric current to flow in a closed circuit. In simple terms, voltage is the force that pushes electric charges through a conductor, allowing current to move from one point to another. The unit of voltage is the volt, abbreviated as V. Question 4. What are the common sources of voltage generation? The most common sources of voltage generation are batteries, cells, and generators. Batteries and cells produce electrical energy through chemical reactions, while generators produce electrical energy by converting mechanical energy into electricity. These devices provide the voltage required to drive electric current through electrical circuits. Question 5. What is the instrument used to measure potential difference, and how is it connected for measurement? The instrument used to measure the potential difference between 2 points is called a voltmeter. To measure voltage, the voltmeter must be connected in parallel with the voltage source, or across the 2 points where the voltage is to be measured. This parallel connection allows the voltmeter to accurately measure the voltage, without significantly affecting the operation of the electrical circuit. Question 6. What is electric current, and what is its unit of measurement? Electric current is the rate of flow of electric charge through a conductor, over a period of time. In other words, current describes how much electric charge passes through a point in a circuit, during a specific amount of time. The unit of electric current is the ampere, commonly abbreviated as amp, or simply A. Question 7. What is the instrument used to measure electric current, and how is it connected in a circuit? The instrument used to measure electric current is called an ammeter. To measure current accurately, the ammeter must be connected in series with the circuit. Because all of the current flowing through the circuit must pass through the ammeter, a series connection allows the instrument to measure the exact current value. Connecting an ammeter in parallel can damage the instrument, and may cause a short circuit. Question 8. What is the unit of electrical work, and what is the unit of apparent power? The unit of electrical work is the watt-second, which represents the amount of electrical energy used or produced over a period of time. The unit of apparent power is the volt-ampere, abbreviated as VA. For larger power systems, apparent power is commonly expressed in kilovolt-amperes, or kVA, and megavolt-amperes, or MVA. Apparent power represents the total power supplied in an AC electrical system, before considering the effects of the power factor. Question 9. How many watts are in 1 megawatt, and how many volts are in 1 kilovolt? 1 megawatt, abbreviated as MW, is equal to 1 million watts. 1 kilovolt, abbreviated as kV, is equal to 1000 volts. These larger units are commonly used in power generation, transmission systems, and high-voltage electrical networks, where power and voltage levels are much higher than those found in ordinary electrical circuits. Question 10. What is the relationship between active power and reactive power? The relationship between active power, reactive power, and apparent power is expressed through the power triangle. Active power, P, is the useful power that performs actual work in the electrical system and is measured in watts. Reactive power, Q, is the power that oscillates between the source and reactive components, such as inductors and capacitors, and is measured in voltamperes reactive. Apparent power, S, is the combination of active and reactive power and is measured in voltamperes. The relationships are as follows. P equals S multiplied by cos phi. Q equals S multiplied by sin phi. South equals the square root of 3 multiplied by voltage multiplied by current. S squared equals P squared plus Q squared. Cos phi equals P divided by S. Tan phi equals Q divided by P. These relationships form the power triangle and are used to analyze power flow and power factor in electrical power systems. Question 11. What is meant by energizing equipment, and what is meant by carrying current? Energizing equipment means applying voltage to a device, or placing electrical equipment under voltage. Carrying current means allowing electrical current to flow through energized equipment, by connecting a load to it. In simple terms, energizing means applying voltage, while carrying current means that the energized equipment is actually delivering or consuming electrical power. Question 12. What is meant by cos phi in an electrical power system? We know that in power distribution systems, the power consumed by electrical loads consists of two components, active power, also known as real power, and reactive power. These two power components have a phase difference of 90 degrees. When active power and reactive power are combined vectorially, they form the apparent power of the system. The angle between apparent power and active power is called phi. The cosine of this angle, cos phi, is known as the power factor. The power factor indicates how effectively electrical power is being converted into useful work. A higher power factor means that electrical energy is being utilized more efficiently, while a lower power factor indicates a greater amount of reactive power in the system. Question 13. What is an inductor? What is its unit of measurement, and can you give an example of it? An inductor is a coil of wire that can store electrical energy in the form of a magnetic field. The voltage induced across an inductor is proportional to the rate of change of current flowing through it. An inductor is represented by the symbol L, and its unit of measurement is the Henry, H. The value of an inductor depends on factors such as the number of turns in the coil and the type of core material used, such as air or iron. Inductors can be connected either in series or in parallel within electrical circuits, depending on the application. Common examples of inductors include the operating coils used in circuit breakers and reactors installed in high-voltage substations. Question 14. What are priority feeders? Priority feeders are electrical feeders that supply power to critical and sensitive areas of the power distribution network. These feeders serve locations where a continuous electricity supply is essential, such as hospitals, emergency services, communication centers, water treatment facilities, and other vital infrastructures. When load shedding or planned power outages become necessary, priority feeders are given special consideration and are typically excluded from power interruptions whenever possible. For this reason, they have a higher priority for maintaining an uninterrupted power supply compared to ordinary feeders. Question 15. Why must high-voltage equipment be grounded during maintenance work? Even when high-voltage equipment is disconnected from the power source, it can still become electrically charged due to its proximity to energized equipment. This happens because the de-energized equipment and the energized equipment act like the two plates of a capacitor, while the air between them acts as the insulating material. As a result, electrical charges can accumulate on the de-energized equipment. If a person touches this equipment, the stored electrical charge may discharge through their body and flow to the ground. This means electric current can pass through the human body, which can be extremely dangerous depending on the voltage level and the distance from nearby energized equipment. For this reason, before any maintenance work begins, all de-energized high-voltage equipment must be properly grounded according to the relevant safety procedures. Grounding safely removes any accumulated electrical charge and protects personnel from the risk of electric shock. Question 16. What is the phase relationship between current and voltage in capacitive, inductive, and resistive loads? In a purely capacitive load, the current leads the voltage by 90 degrees. In a purely inductive load, the current lags behind the voltage by 90 degrees. In a purely resistive load, the current and voltage are in phase, meaning they rise and fall together with no phase difference. In real electrical power systems, loads are rarely purely capacitive, inductive, or resistive. Most circuits contain a combination of all three characteristics. Because of this, the overall relationship between current and voltage depends on the circuit's equivalent impedance, which determines whether the current leads, lags, or remains in phase with the voltage. Understanding this phase relationship is essential for analyzing power flow, power factor, and the overall performance of electrical systems. Question 17. What is the phase angle between phases in a balanced three-phase system? In a balanced three-phase electrical system, the phase angle between any two phases is 120 degrees. This means that each phase reaches its peak value 120 degrees apart from the others during each AC cycle. The 120-degree phase displacement ensures smooth power delivery, balanced load distribution, and efficient operation of three-phase equipment such as motors, transformers, and power transmission systems. Question 18. What is an unbalanced three-phase system? A three-phase system is called unbalanced when the current drawn by the three phases is not equal. In other words, if the load on one phase is different from the loads on the other phases, the currents flowing through the phases will be different, resulting in an unbalanced three-phase system. This imbalance can cause problems such as increased losses, voltage imbalance, overheating of equipment, reduced efficiency, and excessive current in the neutral conductor. For reliable and efficient operation, electrical systems should be designed and operated so that the loads are distributed as evenly as possible across all three phases. Question 19. What is the neutral current in a balanced three-phase star-connected system? In a balanced three-phase star-connected system, the neutral current is zero. This is because the three-phase currents are equal in magnitude and displaced by 120 degrees from each other. As a result, their vector sum at the neutral point is zero. Since the currents perfectly balance one another, no current flows through the neutral conductor under balanced operating conditions. This is one of the key advantages of a balanced three-phase system, as it provides efficient power distribution and minimizes unnecessary current in the neutral wire.
Question 20. What are the different types of overvoltage in an electrical power system? Several types of overvoltage can occur in an electrical power network. The most common types are: A. Lightning overvoltage. Overvoltage caused by lightning strikes, either directly on the system or near transmission lines. B. Switching overvoltage. Overvoltage produced during the opening or closing of circuit breakers and switching operations within the network. C. Ferranti effect overvoltage. Overvoltage that occurs on lightly loaded or unloaded long transmission lines due to their capacitive characteristics. D. Resonance overvoltage. Overvoltage caused when the inductive and capacitive reactances of a system create a resonant condition. E. Ferroresonance overvoltage. A special type of resonance caused by the interaction between system capacitance and the nonlinear magnetic characteristics of transformers or reactors. F. Overvoltage due to contact with a higher voltage system. Overvoltage that occurs when a transmission or distribution line comes into contact with another line operating at a higher voltage level. G. Overvoltage caused by sudden removal of large loads. Overvoltage that occurs when large electrical loads are suddenly disconnected from the power system, causing a temporary rise in system voltage. Understanding these overvoltage conditions is essential for designing protection systems and ensuring the safe operation of electrical equipment.